Hello everyone. Today is our 10th live session. I had previously said that we will start at 3:04, but due to extremely low attendance, I guess I should start this session. So, this today's session we will be just building upon the concepts of the MOSCAP. Wait a second. So, okay, Mr. Vinod has joined. So I was talking that in today's session we will build upon this MOSCAP that we had studied previously. We had gone through this MOSCAP CV briefly, and we had seen that how uh, we can identify different regions of operation like accumulation, inversion and depletion, and we also saw the deep depletion conditions for the MOSCAP. So today we will be solving a few problems about this MOSCAP, and then we will be switching towards the MOSFET, which is our main goal. So let us do some problems which are related to this MOSCAP first. So after that we can start this MOSFET. Okay. So in this problem, okay, we have this n-channel MOSCAP. Rather, I would say I shouldn't say this. This problem is basically related to this MOSFET. This problem itself, it states that we have this 10 nanometer gate oxide, and the substrate sensitivity is given. That is, how does the threshold voltage? Okay, so let me turn off the video first. Okay, so how does this threshold voltage change with the body bias? We are giving some substrate voltage to this system, and as a result of that body bias we are having a change or shift in the threshold voltage, and that is given by this expression over here, which is 50 millivolt per volt. So if we are changing this VBS, for example, by 1 volt, we will be having approximately this 50 millivolt change in the threshold voltage. So this threshold, this substrate bias is given to be equal to 2 volts, and we have been told that the threshold voltage VT is the threshold voltage of the MOSFET, and we have been given that this VBS value is much greater than 2 phi b. This 2 phi b is simply the separation between the Fermi level and the intrinsic level in the bulk, which is simply the surface potential. Okay, this is surface potential, and it is greater than, mostly we denote it by phi f, but in this problem they have given it by phi b, so that's not an issue. So it is greater than this 2 phi f, and we are required to find this doping concentration of this substrate. So we know simply the threshold voltage is given by VTHO plus gamma times VBS plus 2 phi f minus, should be mod rather, 2 phi f. This is the threshold voltage dependency on this body bias. So this gamma is the body coefficient. Okay, you should you must have seen this gamma value, and this gamma is equal to this 2q epsilon Si, since we are in silicon material itself, so it is epsilon Si Na by Cox. Okay, wait a second. So this is the gamma value. So this gamma, as you can see, it is in multiplication with this factor, which is this VBS plus 2 phi f. So, okay, hello, hello, Mr. Digambar. Do you have any question? Okay, no problem. So I was talking that this gamma, it is in multiplication with this factor, which is having the VBS under the square root. So I just for the sake of this consistency or the understanding of these dimensions, I would like to you people to answer this small query or small question for me. So what should be the unit of this gamma? Just by looking at this expression, sorry, just by looking at this expression, what should be the value of gamma? Sorry, unit of gamma. What should be its unit? Okay, so it's a simple. Since this VBS or this fire is having unit of root of volt, okay, so this gamma will be having the unit of root of volt as well, because if we have to add these two quantities, which is VTHO and this quantity given in this red uh, circle, we will be having the unit consistency. There has to be the consistency of units. So this VTHO is having the unit of volt. So as a result of this thing, this gamma will also have the unit of root of volt. So this is just hit and trial. I am not going into this root of 2q epsilon si na, this kind of a thing, and trying to solve its units. I am just saying that just by looking at this expression, we should be able to get a sense of this thing, that it should have units of root of volt. So this gamma will be having the units of root of volt. So it's as simple as that. Now this we have been told to find this sensitivity of this threshold voltage with this substrate voltage or this body bias, this substrate sensitivity. This is dVt by dVbs. So if we derivate this equation with respect to VBS, it would simply be, if I derivate this, it would be dVth by dVbs. It would simply be gamma by 2 root of VBS plus 2 phi f, because VBS is the variable only, and rest can be treated as the constants. This thing will go, this thing will go, so we will be left with this thing, the derivative of this thing only. Okay. Now the second condition was that it is much greater than the 2 phi f value, this VBS. So we can easily ignore this thing. We can say this is equal to root of VBS, because VBS is much greater than 2 phi f. So basically they had given us the surface potential to be equal to 2 phi f, 2 phi f at this point, and this had they had mentioned this q phi b is the separation between the Fermi level and the intrinsic Fermi level in the bulk. And we had seen this thing previously in the previous lecture, that this is nothing but the surface potential. Okay, so this surface potential in this case is greater than this uh, to this VBS bias. So we can easily say that this value is equal to gamma by 2 root of VBS only. This dVt by dVbs is having some value which is 50 millivolts per volt. So it's 50 into 10 to the power minus 3 into 2 times root of VBS. VBS is having the value of 2. Okay, so it's 2. So this is the expression for this thing, and this is equal to gamma. And we can simply say this is 100 into point 10 to the power minus 3 is simply 0.1. It is 0.1 root 2, and this is equal to 2q epsilon si na by Cox. under root. Okay, we know this square root 2 and square root 2 will go, so we will be left with this 10 to the power of and we will square both the sides, so it will be 10 to the power of minus 2. It will be q epsilon si, okay, q times epsilon si and a by cox, okay, or simply it is 10 to the power minus 2 epsilon ox into rather than epsilon ox by t ox, q times epsilon si is equal to na. So this is the value that we require, this doping concentration of the substrate. This is the thing we require. So sorry, so we will try to find this value, and we have been given all these values. This is c ox square, sorry, so it should be epsilon ox square, okay, and t ox square, because it we had squared. Let me write down this thing, squaring on both sides, we get this, okay. This is c ox square, absolutely. So epsilon ox by t ox by q times epsilon si. Now let's look into these values. It is 10 to the power of minus 2. Epsilon ox is, sorry, it is 4 times 8.85 into 10 to the power of minus 14 farad per centimeter, okay. So it is 8 point, so it's basically 4 epsilon ox is 4 times 4 square into 8.85 into 10 to the power of minus 14 whole squared divided by t ox is having the value of 10 nanometer, okay. So it is having the value of 10 nanometers basically. So it is 10 nanometer, or we can say it is 10 to the power of minus 6 centimeter square, okay. Basically if it's 10 to the power of minus 9, it is 10 to the power of minus 7 centimeter, and it is 10 to the power of minus, since it is 10 nanometer, so it's 10 into 10 to the power minus 6 centimeter, okay. Let me rub this, okay. So it is 10 to the power of minus 6 into 1.6 into 10 raised to the power of minus 19, which is the electronic charge, and this epsilon si, it will be equal to, I guess it is 12, okay, it is 12. So it is 12 times this value, 8.85 into 10 to the power of minus 14. So this one 8.85 will go with this one thing, with this thing. So we will be required to solve for this only, which is this 4 squared, which is this 4 squared. Wait a second, let me calculate this value, which will come out to be equal to 4 into 4 into 8.85 divided by 1.6, okay, divided by 12. So it comes out to be equal to 7.35. So let me add the slide. So this NA value comes out to be equal to 7.35 into, let us check this power, it is 10 to the power minus 2, it's 10 to the power of minus 16, so it is minus 16 above, and we will be having this 12 plus 12 plus 19, okay. So this should be its power, it is 12 plus 19 minus 16, so it's 10 to the power of 15, okay. Let me rub this, so it is 10 to the power of 15 centimeter cube. So now let's check the options which are matching, okay. Basically we got this 7.35, which is close to the 7.37, so we will be selecting this 7.37 value. Now let's move towards another problem. This problem is basically related to the MOS cap itself. It says that we have this ideal MOS cap. So we will be having no charges, no fixed charges, any kind of charges in the oxide. So this MOS cap has this boron doping. Okay, since we have this boron doping, it means that this is p-type substrate, and we are forming this NMOS. So let me write this point first. So let me write down this point first. Since we have boron doping, therefore we will be having p-type substrate, and thus we will be forming NMOS. Okay, so we will be forming this NMOS. Now we have been given that this MOS cap is applied some gate bias, and a depletion region of this width, which is 0.5 micrometer, is formed with a surface potential of 0.2 volts. Now we have to find the value of the relative permittivities of the silicon and the silicon dioxide. They are given, and as a result of this thing, we have been told to find the peak electric field which is inside this oxide region. So we will simply try to find the relation between this electric field and this surface potential first. So since we know this is simply the electric field is simply equal to, for this 1D case, it is simply equal to Q times Na by epsilon s. So this we know. So from this, when we solve this and we got the relation for using this Poisson equation and Gauss law, as we know, these are the most vital or important aspects of our, we can say, device physics. So we got this value Emax to be equal to simply equal to Q times Na xt by epsilon s. Now we know this surface potential will simply be the area under this electric field curve. But let us say that this surface potential, which is simply equal to now this, what I can say, it is equal to simply now this. Since if I integrate this thing again, it would simply be, for example, if I integrate this thing psi, in order to get psi, it would simply be Q times Na by epsilon s x square by 2 minus xt, with limits for x for this psi s. If we need to find this psi s at this 2 5 point, so it would simply be equal to this, what I can say, limits between 0 to xt, where we have considered the maximum depletion width, for example. So now this psi s is simply equal to Q times Na by epsilon s xd square by 2. Okay, so from this this relation, which is simply the area under the electric field curve, this psi s, we can easily say that this, we can simply replace this Q Na xt by epsilon s by this, what I can say, by Emax value. Okay, so I would rather say that this psi s is equal to Emax, which is the maximum electric field, into depletion width by 2. Okay, that's what we would have got from this profile. If we had seen this, you had seen this x, if this is the xt, this is the electric field maximum value, you would have simply said the area of this is 1/2 of base into the altitude. Base was xt and altitude was the Emax. Okay, this was the area under the curve, for which is simply the integral. Area under the curve will simply be this integral. So simply we got this value of this psi s to be equal to the Emax times this xt by 2. From this we can get the value of this E max, which is simply 2 times psi s by xd. Now this psi s is having the value of 0.2 volt and xd is having the value of 0.5 micrometer. So it is 2 into 0.2 divided by 0.5 micrometer. So, or simply I would rather say volt per micrometer. Okay, volt per micrometer, which is simply 2 into 0.2 is zero point 0.4, zero point 0.4 by 5 is 4 by 5. Simply, this is the maximum electric field. Now we know that this at the boundaries, when we are at this interface, this we need to have this displacement relation. This displacement relation has to be true. This epsilon s times the electric field in the semiconductor has to be equal to the epsilon ox times the epsilon this electric field in the oxide. This we know. This is by the we know that this electric displacement has to be equal on both the sides. So wait a second. So as a result of this thing, we will be having this relation, that is epsilon s times the electric field in the semiconductor will be equal to the epsilon ox times the field in the oxide. So now this we know this ES value, this maximum electric field value, which we found out was 4 by 5, and this epsilon S, this must be given to us. This epsilon of the silicon is simply 12 and epsilon of the silicon dioxide is 4. So it is 12 times this 4 by 5 times this 4 into epsilon ox. Okay. Now it would simply mean that it is equal to 12 by 5, which is nothing but 2.4 volt per micrometer. Simply, this is the value for this electric field in the inside this oxide for this particular case. So it would mean that this value came out to be equal to 2.4. So the peak electric field inside this oxide region is simply 2.4 volt per micrometer. Now let's move towards the what we can say this important concept that we have all have been waiting for, which is this MOSFET kind of a thing. Till now we were mostly dealing with this MOSCAP structures. We know that when we studied this MOSCAP, we said that this is the heart of this MOSFET. This will be the heart of this semiconductor devices moving forward, and we said that it would help us, this MOSCAP study would help us to go further into the deep insights or the deep understanding of this MOSFET, which is rather vast than this MOSCAP. So this MOSFET is what I can say, it is basically is same the MOSCAP, but it just has two more things attached to it, which is the source and the drain. These source and the drains are basically the two PN junctions which are placed what I can say closer to this gate region. So I would rather say that this MOSFET is like this. It is simply this MOSCAP. Rather, I would draw it like this. If this is my, rather I would say this is my silicon dioxide, for example, SiO2. This was my gate. In the previous case, this is what we have been doing. This was my gate, and this was some gate voltage applied to it. Okay, so basically let me rub this thing first. So this was our, what I can say, this MOSCAP structure, and we had said that we had seen for the p type substrate and the n type substrate. Let's consider p type substrate first, and this is all we had previously. This is all we had. We also had this back contact or this body contact in the previous case. Sorry, let me draw it neatly. So we also had this back contact. So it was this body contact, and we had usually said this body is grounded. Okay, this body contact. Now apart from this thing, these things, we will be having this source region, which will be N plus in this case, since the body is p type, and I will be having another N plus thing. Basically they should be symmetrical. Okay, they should be symmetrical. There is no asymmetry in this thing. Okay, this is the this is the N plus region, or N plus pocket, I would say, and this another is also the N plus pocket, and both these regions will be having some metal contact. Okay, so let us draw this metal contact like this, and this will be known by the name of source, and it would also be, or rather I would say, it would also be grounded. Okay, similarly, I will be having this drain region, and this drain region is having some bias VD, which is this VD is usually greater than or equal to 0 volts in order to have this, what I can say, this device operational. So under the what I can say, operational conditions. Now we have this gate, we have this silicon oxide that we had seen previously, and we have this body. But the addition compared to the previous case is this source and drain regions, these two PN junctions. So basically you can clearly see that this is the p type material over this region. This is p type and this is N plus, so we will be having the PN junctions at this juncture and also at this juncture. Simply we will be having this PN junctions. Okay, simply. So I have not drawn it to the scale, but let us consider that now we will now have some bias applied to it. So basically we will say that, let us first say that if we have this VD, which is this drain bias, if this is equal to 0, if this is equal to 0 volts, so what would happen? What would happen? It would be simple as the MOSFET case, but rather in this case we will be having these pockets of these N plus regions. So the conditions will be same, that we will be having this accumulation as well as this depletion, and then there will be this inversion. So we will say that this when this MOSFET is given drain voltage of 0 volts, and this VG, this gate bias, is less or equal to this threshold voltage, we will be having this MOSFET will be in accumulation. It would be in accumulation or depletion. These are the two cases only. Okay, now if we see now this bias, this condition, so this under this condition, this under this I would say that this MOSFET is now having this bias when we are having less number of carriers, less number of N carriers in this region. Okay, we are having less number of, since we are doing this accumulation or we are doing this depletion. Accumulation would mean that there will be holes in majority at this interface, there will be holes, and depletion would mean that we are just trying to repel these holes, and till now the concentration of electrons is not much greater or not much greater or equal to the value that is desired, that it is not equal to the bulk density of the holes. So rather the electron concentration is less than the bulk density of these, bulk concentration of these holes. As a result of this thing, we will be having the this channel will not be formed. This channel, we will be having no channel in that case, and as a result of this thing, the connection between these two will be missing. This connection between these two n plus regions will be missing, so no channel will be formed. As a result, there will be no movement of the carriers, even if we are applying this what you can say, this bias less than this VT, this threshold voltage. Now if we, for example, now increase this VG such that it is greater than this threshold voltage, so as a result of this thing, we will be having this inversion layer formation. We will be having this charge build up, this electronic charge build up in this region, which will result in the formation of the inversion layer. So rather we would draw this, it would look like, for example, if this is our interface and this was our n plus region, for example, and this was our another n plus region, this was the source, this was the drain. So as a result of this thing, now we'll be having very thin layer. We will be having very thin layer of this inversion, this inversion charge. It would be denoted by this inversion layer simply. And as a result of this thing, we will also be having this depletion region. Okay, this depletion region will be associated with this. Okay, so this is the depletion region simply. And now now if this was the condition when this VD is equal to 0 and this VG, this gate bias, was greater than the threshold voltage of this device, this transistor that we had plotted. Now if we now try to increase this VD voltage, this is the drain bias voltage, what would happen? It would simply attract the electrons, because now the channel, the connection is now between these two regions. The connection with n plus and n plus is there now. So if we increase this VD now, we will be applying, for example, some positive bias over this region. So as a result of this thing, the electrons will be, they will be attracted towards this drain region, and these electrons will move towards this drain region. Okay, because of this, if we apply VD greater than 0. Okay, so this VD greater than 0 will attract the electrons, and as a result of this thing, we would say that the channel, there will be this inversion layer will look like somewhat like this. Let me draw it like this. It would be a bit tapered. It would be a bit tapered. It would be like this. Okay, it would be a bit tapered because we are attracting the electrons which are closer to this n plus region. So this is the n plus region. You must observe that this asymmetrical nature of this inversion layer. Now we are, since VG is being applied and it is in inversion region, and this VD is also greater than 0, the electrons are getting attracted towards this drain terminal. Okay, so if we now continue to increase this what I can say, this bias, this VD bias, so this would result in the special condition which is known by the name of this pinch off voltage. So this, if we apply this, we can say that this carrier concentration at this point would be, at this pinch off point, would be equal to the simply this, it would be simply equal to the bulk doping concentration. Okay, so this is the depletion region for this case. Let me draw this, the depletion region for this case first. And so this depletion region would be something like this, because we need to accommodate for the gate charge. Okay, we need to accommodate for the gate charge. Since this inversion charge in this region has decreased, the depletion charge has to accommodate for the what you can say, the voltage balance. Okay, we need to have this charge balance satisfied everywhere. Okay, so as a result of this thing, this depletion region will grow towards the drain side. Now after this, if we continue to increase this bias, you must have seen in the lectures that this channel will pinch off inside the device, and as a result of this thing, this we will be having something like this. We will be having something like this. This is the N plus region. We will be having, let's say, like this. Sorry, we will be having it like this, like this. Okay, the channel will be pinched off. Okay, there will be no carriers at this point. Then after this, we can have this if the biases continue to increase, this if we continue to increase this VD, if we continue this thing, so the condition might reach that this pinch off point might move towards the source. So as a result of this thing, we will be having no inversion carriers in this region, but the field in this region will be quite high. So as a result of this thing, the carriers which will come to this point will be easily sucked by this field, okay, into this drain region. So this is the post pinch off, rather we would say this is the post pinch off condition, post pinch off, and this is the pinch off condition. This is the pinch off condition. So it would happen at some bias which is VD, which is greater than this VD saturation. Okay, VD saturation. So you must have gone through that, how you can derive this relation between the current and this drain bias and the gate bias. You must have seen the curve will look like something like this. If this is the drain bias and this is the drain current, the curve would look like something this. Okay, so this is after the saturation would occur. After this point, you would say that the current is almost saturated. So let's not go into that much detail of these things, but rather I would say that the expression that you derived, we will be using those expressions mostly now in order to solve the problems. So this is the characteristic that we require, that we will be requiring this um, dependency of this current on this gate bias and the and this, or rather I would say this drain bias and the gate bias. So rather I should also show you the moment of the current. For example, if the electrons are, for example, if the electrons are moving in this direction, okay, electrons are, so the direction of the current would simply be the this, okay, this will be the direction of the current. So it would be into the drain terminal. Okay, the direction of the current will be into this drain terminal. Okay, this will be the direction of the current. It is always the opposite to the moment of the electrons. So the carriers will always move from the source to drain, but the current is from the drain to the source. Okay, so using this concept for this, what we can say, we have seen that the MOSFET can now be in two conditions. One would be in the linear region, that we saw that it can be in linear region or this triode region rather, and it can be in saturation region. Okay, so both the cases are possible for us, this triode region or this linear region. Okay, the this region, and there is another region which is this, what we can say is saturation region. Now you must have seen that in the, what we can say, in the lectures, that you must have derived this current which is having this dependency on the gate and the drain, and now in this problem we are supposed to do the calculations using those equations only. So it says that we have to consider a n channel MOSFET. So n channel MOSFET means the substrate will be p type. Okay, the silicon was p type and we applied the gate bias and we transitioned from the region of this accumulation to the depletion, then to the inversion. And when we were in the inversion region, the channel was formed, and as a result of the channel formation, the connection between two n plus pockets happened. Okay, n plus pocket of the source and the n plus pocket of the drain both got connected, and as a result of this thing, there was the carrier movement, this electron carrier movement. So this carrier movement, we saw that we applied this drain bias, and this drain bias, it attracted the electrons towards the drain, and we saw that how this drain bias increment resulted in the pinch off, and then there was also the movement of this pinch off point into the channel towards the source region, and as a result of that thing, we are now ready to deal with the problems which are related to this saturation or non-saturation regions kind of a thing. So it says that we have this n-channel MOSFET, means that we are having this p-type substrate with the W equal to 15 micrometer. Wait a second. With W equal to 15 micrometer, and the length of this MOSFET, this channel, is simply this 2 micrometer, and the oxide capacitance is 69 nanofarad. So we have to assume this is important. We have to assume that the MOSFET is in non-saturation regime. Since this VDS is very less, it is 0.1 volt only. So this drain current is 35 microampere for a gate VGS of 1.5, and for the 75 micrometer the VGS is 2 microampere, the VGS is 2.5 volt. So we need to find the threshold voltage of this MOSFET using small VDS approximation in the drain current equation. Okay, if this VDS is small, we would simply say this if since VDS is small, we will be in linear region of MOSFET. Okay, we will be in linear region of the MOSFET. So the current would simply be equal to ID would simply be mu n C ox W by L times VGS minus VTH, okay, times VDS. The VDS square term will simply go because we are in linear region. Okay, so now there are two cases in this linear region. One is that this VGS, this gate to source bias, is 1.5 volt. So I would say this ID is simply 35 microamperes, which is 35 into 10 raised to minus 6. This mu NC ox, let me keep it as it is, mu NC ox, and this is W by L. It should also be kept as it is, and VGS is simply 1.5 minus VTH that we require to find, and this VDS is also equal to 0.1. Now case 2 is simply this is equal to 75 microampere. This is mu n C ox W by L. VGS is now 2.5 minus VTH into 0.1. Now what we can do, we can simply divide this second equation by first. So if I do this, we will be simply left with 75 by 35. 10 to the power minus 6 in both the cases will go. Mu and C ox W by L will go. We will be left with 2.5 minus VTH divided by 1.5 minus VTH. So what we have done, we have divided second by first. Okay, sorry. Okay, so we have done this thing. Now 75 by 35, it would simply, rather I should multiply it like this, 75, 35, so it is 25 divided by 40, so it came out to be equal to, this VTH came out to be equal to 0.625 volts. Okay, this is the value of this VTH. Okay, now let's check the options. Okay, there are no options, so the value for this threshold voltage came out to be equal to 0.625. So clearly, if I say this VGS is what I can say, VGS in this case, in both the cases, is in 1.5 and at 2.5. Let us take the 1.5 case. Okay, 1.5 is the case that we are taking, which is the minimum one, which is 1.5 VGS minus VTH will be 1.5 minus 0.625. Okay, so if we do this simple calculation, it would be 1.5 minus 0.625, it is 0.875. Okay, 0.875 volt. Simply VDS, which is just zero point 0.1 volt, is less than VGS minus VTH. So it means that we were correct, the assumption was correct, that the MOSFET is in linear region. Okay, that is what it was given in the problem. So in order to recheck our calculations or recheck our method, we just backtracked and saw that the conditions given in the question corresponding to this answer of VTH equal to 0.2625 are correct. So our assumptions and our, or rather I would say our the approach was correct in selecting this problem. Now this we have this another problem which says that the parameters of p channel MOSFET. Okay, if now this is quite interesting, that this, they say that we are now having this p channel MOSFET. If we are having this p channel MOSFET, now we will be having the n type substrate. Okay, and as a result of this n type substrate, we will be attracting the electron, this holes towards the interface and repelling the electrons from the interface. Okay, so it means that the conditions will be what we can say rather opposite. If for this n type channel where we were having positive threshold voltage, we will be having negative voltage for the p type channel. Okay, because now we have to attract holes, and holes will be attracted by the negative bias towards the interface. So this is simple. So the parameters, the mobility is given to us, it is 310 centimeter square. The thickness of the oxide is given, the ratio of the W by L, and the threshold voltage is also given. Now we have been told by themselves, they have told it themselves, that the transistor is biased in the saturation region. Okay, so if it is in saturation region, we need to find the ratio of the two currents, ID1 by ID2, when the source to gate bias, because gate to source bias will now be negative. Rather, I would write opposite way. I would write, in order to avoid confusions of the sign, I would say that VSG is now VGS is now VSG. That it is just the, we are now attracting the holes towards the interface, and as a result we will be requiring negative bias at the gate. Okay, it's simple as that. Now since this P channel MOSFET is in saturation. Okay, it would mean that ID in saturation is simply 1 by 2 mu P Cox. Now this mu P is the mobility of holes. Okay, mu P Cox W by L VSG. Remember the VG has changed to VSG. Okay, and this will be plus times VTH whole square. Okay, this is the saturation current. Now we are required to find this ID set at VSG equal to 1 volt and VSG equal to 2 volt. I would simply say ID 1 by ID 2 is simply 1 by 2 mu P Cox W by L VSG1 plus VTH, okay, whole squared divided by 1 by 2 mu P Cox W by L VSG2 plus VTH whole squared. This whole thing will go, and we will be left with this VSG1 plus VTH. VSG1 is 1 volt, minus times minus 0.4 is the VTH value. So it is VSG2 will simply be 2. This VTH is minus 0.4. This is the value for this 0.6 squared divided by 1.6 squared. So it is simply, let me check its value on calculator. 0.6 into 0.6 divided by 1.6 divided by 1.6, which is 0.14. So the ratio of the two currents is simply 0.14. Now let's move towards another problem which is related to this MOSFET, and now we are again having this N-type MOSFET. Okay, so this N-type MOSFET, it has this W, which is the width, which is equal to 10 micrometer, and the length is equal to 1 micrometer. Now the oxide thickness is given to be equal to 20 nanometer, and the threshold voltage is simply equal to, what I can say, 1 volts. Okay, now the device is biased such that the VGS gate to source voltage is 3 volt and drain to source voltage is 5 volts. Okay, you must have gone through this thing, that how uh, the conditions on the saturation and non-saturation are dependent on this gate to drain bias, and we have seen that this instance, for this case, let us write down this VGS is equal to 3 volts. Okay, this VDS is equal to 5 volts. Okay, now VTH is equal to 1 volt. VTH is equal to 1 volt. So it would simply mean we would solve for VGS minus VTH, which is 3 minus 1 equal to 2 volts. This VGS minus VTH is less than this drain to source bias, or simply this VDS value is greater than this VGS minus VTH. So it would mean the MOSFET is in saturation, simply saturation, because VGS was greater than VTH, 3 is greater than 1, and also this VDS was greater than VGS minus VTH. So the MOSFET is in saturation region. Now for the same problem which was in question 3, we are required to find the, rather I would say, we have been told to find the value of the transconductance. So transconductance is simply Gm. Gm is the transconductance, which is dId by dVGS, which is the change in the drain current with respect to the change in the gate to source voltage. Okay, this is an important performance metric whenever we are studying any MOSFET device. We need to have this GM value. We need to have this GM value of a proper value, of a proper, what you can say, magnitude, in order to have the gain for the circuit, rather I would say, since you will see that in the circuits part how the gain will depend on this GM kind of a thing, and you will see that this GM becomes really important, and the peak value of this GM, it really determines the circuit performance. Okay, basically this GM, if we consider the physics point of view, it depends upon the density of states of the material. You must have seen in the earlier lectures that we are having some density of states which are associated with the material, and that density of states, we had seen that it had the dependence on the effective mass as well. Considering the parabolic approximation of the bands, we had seen that the effective mass along one transport direction and the another transport direction can be different, and we had seen that this density of states is hugely dependent on the effective mass of the, what you can say, of the material. So this GM also depends upon the effective mass of the material. So in this case, for example, this silicon we are using, we will be having this this effective mass dependency for this GM as well. For example, if we have, you must have heard that there were strained silicon channels which were used in order to enhance the mobility. Okay, the mobility enhancement can be attributed to the change in the effective mass as well, because the strained silicon had different band structure as compared to the actual or pristine silicon. So this resulted in the drastic changes in the uh, properties of the device. You must have heard that when we were scaling down this silicon this silicon based devices, this was a good technique to use. The device engineers used this strain in order to bring this scalability down. So in this case now, this GM is now equal to this dId by dVGS, which is simply the transconductance, which is the important performance metric for us. Now this GM is, then we know this IDS is equal to, in saturation it is simply equal to 1 by 2 mu n Cox W by L. Okay, sorry, VGS minus VTH whole square. Okay, so it would simply be equal to mu n Cox W by L VGS minus VTH. So this is the GM. Okay, now let's put the values for the mu n and Cox extra. Mu n is 300, Cox is epsilon ox by T ox. So I would rather say, so it is 300 into epsilon ox by T ox. This is oxide, it is 3.9 into 8.85 into 10 to the power of minus 14, and this thing, this T ox is 20 nanometer. So it is 20 into 10 to the power of minus 7, okay, into this W by L. W by L is simply equal to 10, okay. So it is simply equal to 10 VGS minus VTH, which is equal to 2, okay. VGS minus VTH is equal to 2. simply. Yes. So now let's solve for this, and let's check the value for this GM. So this is simply 300 into 3.9 into 8.85, okay, into 2 divided by 2. So it comes out to be equal to 1.035 millisiemens. Okay, this is the value of this transconductance. Now, moving forward, it says that uh, okay, that n channel, we have this n channel, rather say n channel MOSFET, and we have this channel length which is equal to 1.25 micrometer, and the mobility of the electrons is 650 centimeter square per volt, and threshold voltage is 0.65 volt. The we have to design the channel width of the MOSFET such that the drain saturation current is 4 milliampere for a gate to source bias of 5 volts. Now, it would simply mean this threshold voltage, this VGS is greater than VTH because 5 is greater than 0.65, and VDS, rather, okay, this VDS, let's assume that the MOSFET is in saturation. Yes, it has been given that the MOSFET is in saturation. Yes, the MOSFET is in saturation. So we would say that MOSFET is in saturation. So the saturation current will simply be given by 1 by 2 mu NC ox W by L VGS minus VTH whole square. So it is simply 4 milliamperes is equal to 1 by 2 mu n is 650, C ox is 69 into 10 to the power of minus 9, W by L, we need to find W, L is 1.25 micrometer, this VGS minus VTH is 5 minus 0.65 whole square. Okay, so if I solve for this, it would simply be 4 times 2, 8 divided by 650 divided by 69, okay, divided by this thing 5 minus 0.65 divided by this thing again 5 minus 65 into 1.25, okay, into, it would simply be equal to 11.78 micrometer. This is the width of the device, that of this MOSFET that we require in order to have the drain to source a saturation current of 4 milliamperes at a bias of 5 volts. Now let's move towards another problem which says that we have to consider a MOS structure with p-type semiconductor, and this p-type semiconductor substrate is doped to a concentration of 10 to the power of 16 centimeter. The thickness of the insulator is given, and the oxide surface charge density is also given to us, which is okay, which is 16 nanocoulomb per centimeter square, and this 5 ms is equal to this minus 0.8. We need to calculate the flat band voltage. Okay, the flat band voltage, we have seen the oxide trap charges whenever we had this MOS cap, we saw that this flat band voltage is simply equal to phi ms minus times this charge divided by the oxide capacitance. This charge in this case, this phi ms in this case is minus 0.8, and the charge density, since it is nanocoulomb per centimeter square, this surface charge density. So I would say that it is 1.116 into 10 to the power of minus 9 nanocoulomb per centimeter square it was, into this 50 into 10 to the power of minus 7, which is this T ox thing, divided by this epsilon ox, which is 3.9 into 8.85 into 10 to the power of minus 40. So let's solve for this value. So it comes out to be equal to minus 0.8 minus 0.2317. So the flat band voltage is simply minus 1.03 volts. Now let's move towards another problem, which is also related to this MOSFET device. This you must have heard that this we mostly use in the silicon, we mostly use the n-type channel. So in here we have also been asked to comment about this. We have been told that this MOSFET device, why is this uh, n channel type better than the p channel type? So the answer to this question is simple. If we consider this mobility, the n channel will have the electrons as the carriers of the current, whereas the PMOS will have the holes as the current carriers. This electronic effective mass in case of silicon less as compared to the hole effective mass. So this results in the uh, much greater mobility in case of the silicon N type as compared to the silicon P type. So the answer to this question will simply be that it has the better mobility. The current carriers in NMOS, as it is written over here, the current carriers in NMOS are electrons, and in PMOS we are having holes. The electrons in silicon have got better mobility than holes. So this is related to the effective mass, and as a result of this thing, NMOS is having better performance in terms of the mobility and than the PMOS. There are materials where the P type or holes will have less effective mass. So in those kind of materials, the P type will be having high mobility. Although mobility does not only depend on the effective mass only, we will be having the electron phonon, also electron phonon coupling also, that would result in the mobility, what you can say, so that would result or that would have the impact on the mobility itself. So this electron phonon interaction will also largely determine the mobility of a material. But in case of a silicon, if we are considering the mobility of the holes is less than the mobility of the electrons. So the n-type channel is mostly used because we require fast operations. Okay, and the carriers we are requiring are the need to move from the source to the drain as quickly as possible. So this n-type channel is having better mobility as compared to p-type channel. Now moving towards another problem. This problem is about the MOSFET again. It says that for the MOSFET, which is shown in figure M1, we have to assume that this MOSFET, we have to assume WBL to be equal to 2, the applied VDD to be equal to 2 volts itself, the K equal to this 100 of the value of equal to 100. So this uh, rather we would say the transistor M1, it switches from the saturation to the linear region when V in is. So we need to find the value of this input voltage for this transistor when this transistor is switching from the saturation to the linear region. So it is as simple as that. So first this M1 is in when it is in saturation. So we are at the edge, basically we are at the edge of the linear and the saturation region. So ID is mu n times Cox W by L VGS minus VTH whole square. Okay, so this is the value for this mu n Cox is 100 micro. So it is 100 micro, 100 into 10 to the power of minus 6. W by L is having the value of 2, so it is simply equal to 2. VGS is simply V in minus source voltage. Source is grounded, gate is at V in voltage, so it would be V in minus VTH. VTH is having the value of, okay, 0.5 volts, so it is simply 0.5 whole square. So rather this is having the value of 0.25. This will be having the value of 10 to the power of minus 4 V in minus 0.5 whole square. So this is the value for this ID. Now this when this M1 switches from saturation to linear, we would simply be having this VDS equal to VGS minus VT. We will be just at the edge. Okay, we will be having this drain bias to be equal to the gate to source voltage minus the threshold voltage. We will be just at the edge. Now it would mean that the voltage is simply equal to VDD. It is simply equal to, sorry, it is simply equal to, if I try to find out this current, it would simply VDD minus V out. V out is VDS and VDS is VGS minus VTH, and it is equal to V in minus VTH. Okay, V in minus VTH. So it is simply equal to VDD minus V out divided by R is the ID. The current, since it is in series, okay, this would be the current flowing into the drain. So I would simply say VDD minus VGS V in minus VTH. V in minus VTH is equal to ID. ID is simply equal to 10 to the power minus 4 V in minus 0.5 whole square into R. R is having the value of, I guess, 10K. It is equal to 10K. So it is equal to 10 into 10 to the power of 3. So we will be simply left with this V in minus 0.5 whole square. Let's take it to this side itself. It will be V in minus VTH plus minus VDD is equal to 0. Okay, this VTH is 0.5 So I would write it to be equal to 0.5. VDD is, let me check, VDD is 2 volts. So let us write this VDD value to be equal to 2, and we will get a quadratic in V in minus 0.5, V in minus 0.5. So it is simply V in minus 0.5 is simply equal to minus 1 plus minus, wait a second, plus minus 1 plus 1 plus it is minus 2 because it is minus 2, 428 divided by 2, it is minus 1 plus minus 3 by 2, so it is minus 1 plus 3 by 2, it is simply 2 by 2 is 1, so V in is equal to 1.5 volts. So it is simply equal to 1.5 volts. Because negative condition we cannot take for this V in, because in that case VGS will be negative. Since we are dealing with this N channel, it would mean that if we are having negative VGS, it would have meant that the device is in accumulation, but we are in saturation. So the positive value of this V in minus 0.5 had to be taken, and we took that positive value and it came out to be equal to 1. We simply added this 0.5 to it and we got the value of this V in at the edge of this linear to saturation region. Now let's move towards another problem related to this MOSFET. So now we are given another problem about this N channel MOSFET, which says that this VGS is equal to 1.8 volt and W by L is equal to 4. The mu N C ox is 70 into 10 to the power of minus 6. VTH is equal to 0.3 and the channel length modulation parameter is equal to VDS. Till now we had assumed that the current in this saturation is independent of the drain bias, but actually it we had seen that how this post pinch off conditions, how they shift the pinch off point from the drain to this towards the source, and we had seen clearly that this would result in the decrease in the channel length. The effective channel length will decrease, as you can see clearly where I had drawn this. Here is the case. You can see that the channel length in this case is, for example, this L, but in this case the L effective has decreased. It is some L, this is the delta L, it is some L minus delta L. So the effective channel length has decreased. As a result of this thing, we will be having this VDS dependency of the current as well, which we had neglected till this point. We had said that this drain to source current is independent of the drain to source bias, but in reality it has some dependence of the on the this VDS, the drain to source bias, which is related to this saturation current by this formula, which is this ID. Let's not go into its derivation, is simply equal to mu n C ox. You must have seen this equation till now, VGS minus VTH whole square. Now, in order to bring the dependency of the drain to source bias, we will be having this thing which is 1 plus lambda VDS, and the lambda will be having units of inverse of the volt. Okay, so this is the equation for the drain current, this in saturation for MOSFET in saturation with drain bias dependency. Okay, so it would say simply now we have to find the drain conductance. Okay, drain conductance. So drain, previously we had seen GM, okay, which was did by dvgs, which was the rate of the change of the current with respect to the gate bias. Now in this case we have to find the gds, okay, which you have to find the gd. So this gd is simply the rate of change of the drain current, sorry, with respect to the drain bias, drain to source bias. So this is the drain transconductance, or drain conductance rather, I would say this is the drain conductance. Okay, so simply if I derivate this equation, we will simply get this equal to 1 by 2 mu n C ox VGS minus VTH whole square will remain as it is, times this whole thing will be multiplied by lambda. Okay, so let us put the values. It's 1 by 2 mu n C ox is 70 into 10 to the power of minus 6. VGS is 1.8. VTH is 0.3 whole square. Lambda is 0.09. Okay, so if we try to solve for this, it would simply be 70 into 1.8 minus 0.3 minus 0.3 whole squared into 0.09 divided by 2. It is, have I forgot something? Have I forgot something in this expression? Because my answer is not matching any of the options. Okay. Okay. Where is the W by L? Where is the W by L? W by L we have forgot. W by L, W by L is there as well. So the W by L is 4. Okay. So it is 4 by 2. Okay. So now our answer will be correct. So it is 28.35, which is this value, 28.35. 28.35 microsieverts. Okay. Microsieverts is the answer. So W by L was there, which we had missed while writing down the formula. So it's okay. We arrived at the result just at time. Otherwise, we might have missed this W by L value. Now, moving towards another problem, it says that this problem is related to the N-type MOSFET, and it has been shown to us that this conduction parameter is given to us and is equal to 0.249, and this VGS is 2 times VTH. So VGS is greater than VTH, and this is, it is greater than this. VGS will be 1.5 volt. It is greater than this 0.75 volt, and assuming that uh, this MOSFET is in saturation, let us consider the MOSFET is in saturation. So if we take the equation for this ID, it would simply be 0.249 into 10 to the power minus 3. VGS minus VTH will be 1.5 minus 0.75. It would be 0.75 whole square. So it is 0.75 whole square. It is 0.75 into 0.75 into 0.249. It is 0.14 milli. It comes out to be equal to 0.14 milliampere. So this is the value of this current. This is the ID. A simple problem. Now let's move towards another problem, and it says that we have, I guess this is bit good problem. Okay, it says that we have this n channel MOSFET, and it has these parameters which are given to us, and now the condition on the gate to source bias is that VGS is equal to 3 minus 2 times sine of 4t. So since VGS is equal to 3 minus 2 times sine of 4t, this current will be maximum when VGS is maximum. You must have seen the condition that this VGS uh, will have this dependency. This current is having the dependency on the VGS minus VT. So if this VGS minus VT is more, the current should be more. This logic is simple behind this statement. Okay, the logic is simple that if the current is more, the VGS has to be more. Simple. So this VGS maximum would occur at when when this sine of 4t is equal to minus 1. So if it is minus 1, so VGS max is simply equal to 3 minus 2 times minus 1, which is 3 plus 2 is 5 volts. Okay, this is the maximum value of the voltage. Now VDS is simply equal to 1 volt. It is given to us here, and VTH is also equal to 1 volt. So now simply this this VGS is greater than VTH, but it is less than VDS. So it would mean that the device is in, since this VDS is less than VGS max minus VTH, which is this 5 minus 1 4. Okay, so the device will be in linear region or triode region. So device will be in linear region. So let's write down the equation for the current, for this maximum current that we would get. It would simply be this 1 by 2 mu NC aux W by L, this 2 times VGS minus VTH times VDS minus, this will be VGS max, okay, minus VDS square. Okay, so this is 1 by 2 mu n is having the value of 1 milli. Okay, 1 milli, so it is 10 to the power of minus 3. W by L is having the value of 10. Okay, 10 times this 2 into VGS max. VGS max is 5 minus 1. VDS is 1 minus 1 whole square. So it is 2 into 4 into 8. 8 into 10 is 80. 80 divided by 2 is 40. Sorry, it is 2 into 4 is 8. 8 minus 1 is 7. 7 divided by 2 is 3.5. 3.5 into 10 is 35. It is 35 milliamperes. So it is the maximum value of the current that we can obtain. So it is 35 milliamperes. That is the maximum value of the current we can obtain. Okay. So this is the correct option to go with. Now Let's move towards another problem. It says that we have to assume that the subthreshold current of the device of the MOSFET in amperes is given by this expression, which is ID equal to 1.5 10 to the power of minus 15 into exponential of VGS by 2.1 VTH. And this is over the range of VGS is between 0 to 1 volt. And this means that we have to take this interface states into the account, and this the value of the thermal voltage is 25.9, and we have to assume that there are 10 to the power 6 identical transistors on a chip which are all biased at the same gate to source voltage, and VDD equal to 5 volts. Okay, now let us try to solve this. It would simply mean that at VGS we need to find the ratio of the current at VGS equal to zero point 0.7 and VGS equal to zero point 0.5. So this current at VGS equal to zero point 0.7 would simply be equal to 10 to the power of minus 15 exponential of zero point 0.7 divided by 2.1 VT H. This is VT, this is not VTH, this is VT thermal voltage. Okay, and ID2 is simply 10 to the power of minus 15 exponential of, which is zero point 0.5 is the VGS by 2.1 VT. Okay, so if I divide these two, I would get ID1 by ID2 to be equal to exponential of 0.7 minus 0.2 divided by 2.1 VT. So it is exponential of 0.2 divided by 2.1 into 25.9 into 10 to the power of minus 3. So let's solve for this. It is 0.2 divided by 2.1 divided by 25.9. It will be into now 10 to the power of 3 exponential of 3.677 exponential of 3.677. It comes out to be equal to 39.5. So this value comes out to be equal to 39.5. Okay, so the option C is the correct option to go with. So I would like to stop here. So Mr. Vinod, I guess you are the only participant in this meeting at present. So if you have any question, you can ask me. Uh, Otherwise, we can end this session of ours. So if you have any suggestion as well, you can speak. Okay. Is Silvaco Atlas coding for MOSFET? Wait a second. Okay, is Silvaco Atlas coding for MOSFET tunnel FET? What? Go TFET. How to start? Okay. Mr. Vinod, I am not having that much expertise in this Silvaco Atlas, but still I would suggest that all these things are present in the examples itself, these tunnel FETs or even the simple FETs or the GaN HEMTs or the gallium arsenide HEMTs based devices, even the diodes are present in the examples in the Silvaco Atlas. Although I don't have that much expertise in this, but I would suggest you to go through the manual first and then the examples. If you read these two things by what I can say, uh, by the purpose of understanding every point, you will be easily able to locate everything. You will be able to even employ your own device physics by making some unique structures as well. And exploring the device physics is always there with this with these TCAD based tools. You can always learn that. So I guess the manual will be the best thing to go with, and followed by the examples that are present. Because if you are trying to do these device physics kind of a things, you must have some knowledge, because you are already are doing this course. You must have built some good knowledge about the device physics, and I also know that you must have previous knowledge, previous good knowledge as well. So it means that if you are for example getting some trap model in these kind of codes, you will be able to build the insights that you have gone through the courses in your, for example, lifetime. You must say that this kind of trapping I have seen, okay, this is this kind of a trapping mechanism that should occur, or this is this kind of tunneling mechanism that could occur at this particular channel length or at this particular bias. So you would include that particular tunneling model, or you would include that particular trapping model. So it goes like that. You have to go through the manual. You have to keep the device physics of these structures in mind, and as a result of that, you will be able to solve, I guess, every problem that you will face in this Silvaco Atlas or anything. Okay, Mr. Vinod. If there is any other question you can ask, I am I will be happy to answer. But if we do not have any question, we can end this session. So if you do not have any question further, I request you to leave the meeting. And otherwise, if you have any question, we can answer the question again. Okay. So I guess that that's it for today. So let me end today's session. Thank you for joining the session. Let's hope and meet in the next session with these new problems, and let's hope that these sessions enhance our understanding further.